All right, I want to go through, I think in less than 10 minutes, the structure of the system we're talking about. Okay, so we're starting out with the simplest possible manifold, but we're trying to get all the characteristic details of that manifold resolved. Okay, so we're starting with the Giesking manifold, and specifically we're taking 2 times the Giesking manifold, which is equal to the hyperbolic figure 8 knot. Now, when we look into the structure of the hyperbolic figure 8 knot, meaning this is the internal gap that we're creating in our gapped system, our hyperbolically held together, balanced, invertible system, it's going to have this as its internal gap. We want to know exactly what the structure of that is and what its external complement looks like what everything on the outside of the gap is doing that falls in towards it. So we're going to look more closely. Say the hyperbolic figure 8 knot is equal to I, the imaginary number, imaginary unit, times by 2 dilogarithms. We're going to take the difference of 2 dilogarithms. So it's bipart dilogarithmic structure of 1 over the imaginary golden ratio minus dilogarithm of the golden ratio. Okay, now of course, real quickly, the imaginary golden ratio is equal to -1 to the 1/3, and I is equal to -1 to the 1/2. Okay, so this is just a two-dimensional, a polylogarithm, okay, a two-dimensional logarithm under a specific, really beautiful argument, one that has a lot of symmetries, right? With this thing cubed is -1, just like this is squared is -1. So both of these are playing a role in the structure of our hyperbolic figure 8 knot, which is playing the internal gap of our hyperbolic system. And we want to know what the external part is going to be now. Well, we want to mirror this structure here to get the real projection on the outside. So we're going to drop the I, and we're just going to ask, what is Li2 of 1 over the imaginary golden ratio minus Li sub 2 of the imaginary golden ratio? And that's the same thing I wrote over here, but now I'm going to put a plus. We're just changing to see what the external component of the same structure looks like and see what it is. And beautifully, we get 4 pi squared over 288.
Oh, that's a cool thing, just taking out the I and making it plus.
Yeah. So these two structures are complements of each other, okay? They're internal and external. And the nice thing to note here is we're saying we have a sphere squarely maintained divided by 288. And you might remember the hyperbolic figure 8 knot has the symmetries of the tetrahedron. And the generalized formula for the volume of the tetrahedron is something like volume squared is equal to 1 over 288 times by the determinant of a 5 by 5 matrix, okay, with all zeros down here, so it's invertible, and ones here, so it's unitary base. And then we have 6 different components, which are just the different distances in your tetrahedron's edges. So if you draw any tetrahedron, it's going to have 1, 2, 3, 4 vertices. And those 4 vertices connect via 1, 2, 3, 4, 5, 6 edges. So there's 6 edges involved. So the 6 edge lengths go there and then mirrored here. You can put them in any order you want, as long as it's mirrored from here to here. Anyway, this is the general formula for the volume of a tetrahedron, any kind of tetrahedron, okay? And the hyperbolic figure 8 knot, of course, has been famously found by William Thurston to symmetrically be reduced to the tetrahedron, so directly connected here. And now we're finding that the external, the inverted part of the same structure here, same complete system under the same arguments, and gives us something that's exactly reminding us of the poster we have here. Right? We have a poster that's, we think, projecting out to a sphere on its outer edges. And the internal structure of that sphere is all hyperbolically bound. So it breaks up into many kinds of boundaries, all hyperbolically maintained. But that structure is 1, 2, 3, 4, 5, 6, 7, 8 rows of equations, and there's 36, like down this way, and 8 rows of 36. 8 times 36 is 288. So what we think is going on is that the system that's simplest to possibly make, that's a system that's perpetual, a system that once you've created it, it keeps creating itself. So the simplest version of that is the Giesecke manifold double covered. Okay, so once we've got that formed, now what does the outside do in response to the fact that you formed that thing, the simplest possible thing that inverts about itself? Okay, it's going to do this. It's a sphere that's divided up in 288 ways, a squared sphere divided up in 288 ways. Okay, this is exciting for us because we've been looking into all the equations for the constants of nature. And actually, a couple other things before I go there. So what we want is the entire set of characteristics of this system, internal, external system. We want to know what all of the 288 connecting pieces or division structure geometries are, how the whole thing connects. That's what we want, okay? One side note, if we change this equation by putting I in here and there, so 1 over I and I, then this equation changes from being hyperbolic figure 8 naught, which is 2 times GGI, to being 2 times Catalan constant. Okay, so the Catalan structure is symmetrically maintained in this system at the same time. Like the structure is the same, it's under a different argument, that's it, different rotation. What else did I want to say? Okay, let's go now to how we think the picture of this looks. The details we have so far of how this external projection of our bipart dilogarithmic structure looks, okay? And it's going to be the simplest possible hyperbolic system that can exist. It's rooted on the simplest possible 3 manifold that can be according to geometry. Okay, so this is a beautiful start. Now we just want to reveal all these different pieces. Okay, so how we start is we say on the outside, we believe at first approximation, we're just making things hyperbolically connected. 1 over x plus x cubed. Why? Because we formed the hyperbolic figure 8 naught. So outside the reach of whatever you've connected is going to hyperbolically reach. And this is just the trivial hyperbolic equation. Okay. Now, if you set this equation, this reach, equal to 0, then you're asking where are the roots of this connection? Okay. So we're looking for the roots, and the solutions are x equals the imaginary golden ratio, 1 over the imaginary golden ratio, and imaginary golden ratio squared, and 1 over the imaginary golden ratio squared. Okay, so this helps confirm the story that we were starting with, that this is connected to the internal gap that we've made, all right? Because it has the exact same roots as the rotation argument of our bipart dilogarithmic structure. So, okay, it looks like it's the same form on the external reach. But we don't want this thing to reach out forever. You know, it's breaking up into lots of parts. We need the system to rotate and twist about and connect about one of those parts. It has to somehow rotate and fit into itself along some of the existing boundaries it creates so that it can anchor itself, right? That's what we need. We need some boundaries to come up against each other, and they make an anchor in the system so it doesn't fall apart. It has stability. All right. So we're going to take this simple hyperbolic external reach of our hyperbolic figure 8 naught gap, and we're going to modify it just by giving it one anchor. right here. One circle is put into the system. That's one anchor. This is the simplest possible anchor you can make. Anything less than that would fall apart. Okay, and now how we're imagining this is we're creating a hyperbolic projection, which means if you're looking into the inside of this projection, you're going to see boundaries that conform to the hyperbolic structure, the conic structure, right? The internal one is going to be this cone on cone. There's going to be another kind of boundary here and here, goes all the way around and connects to there, and all the way to the back and connects. So it's a single sheeted hyperboloid, and another one here and here. These are both considered one boundary, the top and bottom pieces. Okay, so they're thought of as connecting at infinity in the back. Okay, we could go further by zooming out now from our hyperbolic knot on the inside. And this is twisted. Okay, thinking the cone is where the twist happens. But if we zoomed all the way out, eventually the thing would become just a sphere. Okay, so there'd be some boundary that if you went outside the boundary, you're now outside of the system. You're not in the balanced system that the knot created. And therefore none of the rules apply anymore. You have to be in that system for the rules to apply. Okay. Now that we've modified our system with this single internal loop, we want also, note when I drew this, I drew it with a gap already. You could imagine if I pushed these together, then the angle of the cones gets wider and wider, all the way until they touch. And at this point where the cones touch, these points also touch. Okay? Which means you've kind of taken it to the infinite limit in which it no longer makes sense. Which means the hyperbolic structure you're trying to reveal is no longer revealed, is what I mean by no longer makes sense. You can't see the structure anymore at that point. But everywhere else you can. So I've given it a point where we have an actual positive gap, and with that gap, we're no longer going to set this equal to 0 to find our roots, because we've modified our root structure by now we're fitting into a gap. Okay, we're not fitting at 0 anymore. Okay, so now we're going to represent this by I to the j or I or k to the negative pi over 2 minus the gap size in our hyperbolic space. So that's what characterizes the specific hyperbolic space you're picking, right? Since every hyperbolic space is similar to every other one in the way that they connect in this conic structure and that they form these boundaries and these boundaries. It's just the scale of the structure that changes. So if you pick a specific scale, now you've locked in the rules and relations of the entire hyperbolic space. All right, here, MP, we're putting in the Planck mass. The Planck mass, the gap of mass in hyperbolic space. Okay, and this change of going from 0 to fitting in our own structure so that we can close and persist alters our roots to now being numbers we call J1, J2, J3, and J4. All right. Now, surprisingly, we're almost done. What do I mean? I mean, we want to get a picture, we want to get a system where we can look at the details of all 288 ways that that structure divides, the external projection of the simplest possible internal hyperbolic knot. We want to know all the ways it fits and connects, okay? Well, you wouldn't think we're almost there, but it turns out these numbers are very magical. Very magical. Now remember, we're trying to divide a sphere. Okay, so these numbers need to have some sort of relation to a sphere. And it turns out they have a beautiful, in fact, I would argue they might have the most beautiful connection to spheres that we've ever seen so far. And look what I mean. If we take the first root and add it to the second root, add it to the third root, and the fourth, we get 0. So we get a balance. Okay, beautiful start, a thing to get. But think of this as an equation that tells you have a balance, a 0, that's 4-part. It's a 4-part 0. Now, instead of taking the sum in an algebraic system, you're interested in the ways these things fit together. And the simplest way to check how the system itself in whole works is by checking the sum of its roots and the product of its roots. And in this case, the product of the roots is 2 pi. This is a really gorgeous story so far. We have a 4-part 0 and a 4-part circle. The things that are doing the 4-parting in both cases are the same things, but they're doing different things. We're adding in this case and we're multiplying in this case. This is a fantastic start. This should be enough to get anybody interested. We have an algebraic hyperbolic structure that's 4-part circle and 4-part 0 in this case, in this story so far, but it's more. If we square them and add them together, we get another reveal of a 4-part pi, in this case a 4 pi, negative 4 pi. So I'm telling you these 4 magic numbers, which are the roots of the simplest possible hyperbolic projection of the simplest hyperbolic knot, fit into itself along the Planck mass gap. That's the scaling parameter of the system that makes that work. Okay? The roots of this have this relationship to circles and spheres.
Very cool.
And very central. This is the whole story for how the external system under this connection connects. Okay? And by whole story, I mean it's got all 4 pieces in it. So it's telling the whole story. That's why you get a balance and a circle and a projection of a sphere. Perfect. But what we're interested in now is, just now tell me all the partial stories contained in it. All the partial stories of this partition structure, of this simplest possible hyperbolic space. Okay, how do we know what that is? Or what do I even mean by the partial structure contained in it? If you think of these in terms of actions or vectors being added together or multiplied, okay, then when you put one vector together with another vector, you can do tip to tail, okay? And after you do more than one of them, the end result is the same thing as if you would have started at the beginning and went straight to the end point, no matter how it wiggles around, okay? There's a new arrow that shows you the total action of all the added arrows. Okay. What we're interested in is any total action that's just single dimensional. And by single dimensional, I mean it has a one-dimensional output, not a complex number. It's not a two-dimensional output, it's a one-dimensional output. So it means we can associate it to a single, unique magnitude and kind of action in the partition structure. Okay, it's available to this set of rules without breaking them. Great. So it turns out it's pretty simple to see the list once you know that 3 and 4 are antisymmetric complex numbers. We can take combinations of J1 plus J2. That's a partial set of the structure. And in order to be a partial set, you have to be plural. You have to take more than one thing and put it together and do something with it. So here, J1 plus J2, when you add those two numbers together, you get a single one-dimensional output. So that one counts. J1 minus J2. Anytime I put a plus, you can also take the mirror one. We're going to take the full sets of ones that work. Okay. But if we take 2 plus 3, you get a two-dimensional output, so that doesn't work. 3 plus 4 turns out to be not one-dimensional output because the complex part or the imaginary component of 3 and 4 are exactly opposites of each other. Too much helping, kitten. Let me hide that one. Okay. Okay, so if we take the list of the 2-part and 3-part sums and products and quadrances, see, this is the full system. Just take the 2 and 3 parts of the sums and the 2 and 3 parts of the products and 2 and 3 parts of the quadrances. And that's the partial partition set available to this minimal projecting sphere. I hope that was clear. This is the story when we tell the story with all of its pieces. Every action at the same time. We get these 3 kinds of things that are happening. When you want to ask, what does this same structure do partially, meaning what are the internally available actions in this structure, then we just gather all the 2-part and 3-part, that would be plural, but not 4-piece, because that would be the full ones. So 2-part and 3-part of each of these 3 equations, of the sums, of the products, and the quadrances. And when we list those out, we now have the partition grid of the minimal possible hyperbolic structure. Okay? And all we have to do to check to see if nature happens to line up in any way with that minimal geometric structure is to ask every single constant of nature, do you have a relationship with this particular piece? Grid out all the pieces and ask. And we go on Wolfram Alpha and look for the simplest closed form available, if there are any. And magic happened. Absolute magic happened. Not only did we find a pattern revealed in the constants of nature, not only did we find a pattern, I think it's a pattern that a complete novice can see. Now, if you've never seen this before, I want to ask you, can you see a pattern in the constants of nature? Because I want you to know, the greatest treasure science has ever been after is to figure out the structure of reality, the rules encoded in atoms, right? It took us all this time to figure out that there were atoms, that atoms connected, and there were certain rules to the connections. But right now, at this point in history, we have a collection of the data points, of the rules. We have some equations in physics that connect actions and transform from temperature to energy and so on like that. But the entire system of how all the transforms work and fit together, we don't have that system right now in our story, right? We're completely lost with why the constants are what they are. The parameters that put together the world that we find ourselves in. The parameters that atoms always adhere to. Okay, what I'm saying is, we now have a simple story for how the simplest possible internal hyperbolic knot forms to create a gapped system. A gapped in what? A gap in an external projection that's hyperbolically also bound. Okay, so this is the external part of the story. This is the internal part of the story. And the external projection is going to have 288 expressions, 288 ways that the system's being divided up. And each of those ways will uniquely carve out a scale, a size, and a kind. The kinds don't have to be unique, but each one has to be at least unique in scale or kind, okay, of the 288. And now that we've looked to check all those division parameters, the partial sets of the division system against the constants of nature, let's see what pattern emerged. Let's see if you can see a pattern in what emerged. All right, let's switch over to this one. All right, so this is where we're starting, our hyperbolic partition equation, right? This is our external division connection in our projection of the hyperbolic figure 8 knot. And it has a product of 2 pi, a sum of 0, and a quadrant of negative 4 pi. Okay, now the partial sets of the product, sum, and quadrants are going to give us our structure, our division structure for the system we're going to check against.
So those are the 8 columns of 36 components.
Yep, 8 columns, 36 each, which is 288. So there's 288 partial expressions of that system. Let me start from the far right side and show you what I mean. Okay, there we go, nice and big. All right, in this system we have, it's a division structure attached to J1 squared plus J3 squared plus J4 squared. That's a 3-part quadrant, okay? And you could also have a 3-part quadrant that had J2 squared instead of J1 squared, so that's another available one, or there could be minuses.
And this is one of the available partial sets.
Yep, one of the available partial sets. And you can see we have 1, 2, 3, 4, 5 equations on the screen. And these equations on the right-hand side, between these parentheses, are almost identical. We have a plus sign here, a minus sign here, a plus sign here, a plus and a minus. So other than the signs, they're exactly the same. This p is the plastic constant squared. Okay, and that's it. So it's using the plastic constant in a square way against a three-part quadrants on the right-hand side for all 5 of these expressions. Now these are 5 different constants of nature. These spit out numbers with dimensions that exactly match and therefore predict complete all the rest of the digits that give closed forms for the constants of nature. And they're closed forms based on the partial division system of the simplest possible hyperbolic projection. Okay.
Now for those of us that haven't maybe joined before, or maybe this is a little bit newer to them, their first intro there, maybe just kind of break down the structure of it. So we have we had our sets over there on the board you went over. Now we're doing partial sets as a group structure, but we also, outside the parentheses, the plastic constant and everything, we also have some dimensions and some other stuff.
Okay, so every single equation, this is good, thank you. Every equation is going to have, on the left-hand side, it's just a symbol. Okay, that's going to be the symbol for what we're talking about. Here, C2 is the second radiation constant. Okay, and then on the right-hand side, it's an equation that tells us a closed form that gives us that constant. And its dimensions too. And we get there by multiplying an action, a geometric action on the left, by some set of boundaries. In this case, it's the Planck length and the Planck temperature.
Yeah.
Okay, 2 pi multiplied by those 2 boundaries. And that gives us the right dimensions for this expression, but not exactly the right number. It gives us about the first 7 digits of the right number. And we're about off by exactly this in each case. Okay, so it's a 2-part structure where it takes both pieces to make this make the number exactly right, which tells us a lot about the balance system as it is. Now, on the right-hand side, we have an action against a partition set, and these partition set will always be a partial set of the Js.
Right.
Any partial set of the Js that gives us a one-dimensional output. And then this symbol here represents the magnitude of the Planck length times by the Planck mass divided by the Planck charge squared. It's a central scaling factor that represents the actual picture of our conic cone-on-cone picture. That's the inversion boundary. Those 4 boundaries connect to make that structure exactly like that. So on that scale, when we zoom into that scale, the cone-on-cone is exactly 90 degrees, or if you look from the x-axis and y-axis, 45 degrees, right? It looks just like that, actually, on that scale. So that's a really good symbol for it. But in each case, this box with the x going through it represents the inversion boundary of our hyperbolic system, and it's equal to the Planck length times by the Planck mass divided by the Planck charge squared. And then you take the magnitude.
For those of you that may wish to play around on Wolfram Alpha, it's a free website. Basically, that magnitude for our partition there, the Planck length times the Planck mass over the Planck charge squared, if you look it up dimensionally, it's going to be called Ampere's constant. It's approximately 10 to the minus 7. Many people believe it's precisely 10 to the minus 7. We have some evidence that suggests that it's almost that. That does make a difference once you start getting up to 12, 14 significant digits.
Yeah, it's a very interesting number too, but that 10 to the negative 7 offset in the structure of the constants of nature is something many people have found. I think more people are starting to find too, which is very interesting conversation there, yeah. All right, here's another set of 4 constants. The same exact rules apply. Are we on the same Js? We changed here. Instead of plus, we're at minus, but we're still at J1 squared, 3 squared, and 4 squared. Okay, and there's some symmetry in these equations with the group above, but let's just look at the symmetry in the equations themselves in this set. It's the same numbers all the way through, but we have plus, plus, minus, plus. So just like above, it's only varying by the sign. And on the left, we're using the same 2 boundaries each time. Planck time, Planck temperature, Planck time, temperature, every time. Sometimes in numerator, sometimes in denominator. All right, and we have 2 pi. In each case, a Kelvin, which means 1 Kelvin, okay, 1 second. So the unit Kelvin, the unit second are playing a role in the construction of the constants of nature. Of course, this is the constant of nature we call the Hertz-Kelvin relationship. And Hertz is 1/2 second. So you can think of it as the 1/2 second time the Kelvin relationship. And this is the Kelvin-Hertz relationship. But it's nice to get exposed to this concept if you haven't. The Kelvin, the second, the meter, the kilogram, the units themselves are the ones of the division structure. Really cool. All right, here's another set of equations. Now remember, what we're saying here is that when you plug in these numbers, you get an output with dimensions that match the constant of nature. So we're using this division structure to reveal the pattern in the constants of nature, which gets to tell us what? How they're connecting, what the shape looks like. It'll make it possible for us to see the actions that are responsible for the thing we're calling the constant of nature. And the constants of nature are responsible for all the actions that occur. There are no transforms in reality that don't involve the constants of nature.
You kind of need reality to make up reality.
Yeah,
if we can start to map it out. That's a very good step.
So this is a beautiful. I mean, so this is the time to pose to the audience here. Do you see a pattern in these constants of nature? I'm asking you to trust me at this point, I guess, that this actually produces the right number for the constant of nature. But given that that's true, do you see a pattern? I mean, I'm going to attach at the end of this video a copy of this poster. It's high res, so you can zoom in, you can check it out and try to check out the pattern for yourself and let your curiosity build. Why is nature built like that? But I'm also going to attach the file that defines each constant of nature with the name and the numbers and so on. So the full set of information. All right, so let's look. We have on the right-hand side 18 times the QRS constant, or CQ, and J1 squared, 3 squared, and 4 squared, and they're being added together. So it's a 3-part quadrant system again. This whole column is 3-part quadrants. That's how they're organized by that. So it's not by accident. And every time it looks like it's the same sign, same sign, same sign. Yep. The right-hand sides are identical in every piece in this group. And how many are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oh, and there happens to be a 12 in one of them. That's kind of a nice symmetry. Okay, without knowing anything about what they are, you can totally tell that they're all connected, at least on the right-hand side. I hope. On the left-hand side, is there a pattern there? Well, if we look at the far left of the parentheses here, they're again exactly the same. Every single one. 6 over e to the Euler-Mascheroni constant, J1 squared, which is the fine structure constant. Okay, and this ratio 6 over e to the Euler-Mascheroni constant is a constant that's embedded in the primes. Okay, in the structure of the primes in a simple way. So we got a prime structure connection with the fine structure constant, defining all of the left-hand pieces of this connection. So this is a clue to maybe what's going on. What about inside the parentheses?
Well, inside there, basically everything is the exact same except for the numerator there, which is mass. Yeah,
good. So here we have the Planck charge and the Planck mass. And when you put them together with these, that makes a mole. This is a mole. And now if you tap on the electron, it's a mole of electrons. And you have a mole here again, it's the same thing. Now a mole of muons, and a mole of atomic mass units, a mole of protons and neutrons and tau and deuterons and helions and tritons and alpha particles. And then here, molar mass of carbon 12. It's 12 times, where did it go? This one. By the way, these are all in numeric order also. So if you were to spit out the numbers instead of the symbols with the scales, they're all exactly in numeric order also, which is kind of cool to look at them sharply like that. All right, keep going down the column. Just pay attention to on the right-hand side, these are all 3-part quadrances. Okay, if we move to the next column over, these are all going to be 2-part quadrances. And I hope, I'm going to move kind of fast now. We're not going to go through all of them today. I'm going to make it available for people to go through. But the big thing is we have a simple story developing in which we start with the simplest possible internal gap that a hyperbolic space makes available, defined by the Giesecke manifold. You double cover the Giesecke manifold itself to make the hyperbolic figure 8 knot, and now you've twisted the domain into a hyperbolic system, the minimal hyperbolic system, and you want to ask, what is the external part? Everything that is in response to what you just did. You want to know, what does the system on the outside look like and do? And these constants of nature seem to be lining up in a very beautiful way, in a way that reveals some very symmetric and centrally important. Pup is the universal parabolic constant. It's the brother to pi, right? Pi is the universal circular constant. Pup is the universal parabolic constant. So we call this puppies that overate. Right? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 puppies that overate in this system. And what are these? This is the Compton wavelength. And these are all the wavelengths of the different particle masses, right? I mean, every mass can be converted into complete light, to energy, right? And this is the wavelength. This is the Compton wavelength and all the other wavelengths down. Then we got the inverse meter kilogram relationship, the kilogram inverse meter relationship, the inverse meter atomic mass unit relationship, and so on. And these are the reduced versions of the same thing. So 14 things pop out, simple pattern, simple, beautiful pattern. If that's all you're seeing, I want you to know how important that is. To see a pattern in the constants of nature. That's what gets you to figure it out, right? I mean, Kepler didn't derive the laws of physics. Kepler looked for data points and saw a pattern in the data points and found a pattern. And that led him to then understand things and use that pattern to do many things conceptually, right? But it was a great starting point. Later, Newton came along and derived Kepler's laws, right? From underlying principles, from concepts. But had Kepler not made those concepts important, nobody would have been trying to derive them. So looking for the pattern in science is the major step. We're always looking for the pattern in data points and things we can measure, in things we can trust, right? Measurements are the most trustworthy things. These are closed forms, so they give you exact digits, not just the ones we've measured. They continue giving more digits, so you can ask questions of them as far as you'd like to prove them wrong or to whatever, right? You can look into it further because there's more of a claim being made.
Now you have a limit you can accept.
Yeah, yes, exactly. All right, so let's keep going up the column. Remember, we're on the column of two-part quadrances, okay? These were all 3s and 4s, but they're minuses. I don't know if you noticed, but they're all negative. Okay, and then we have one that's positive. There's a lot of story to follow, and you can just try to plug in the universal parabolic constant on Wolfram alpha and start investigating what it is, and you'll be more excited. Let's keep going though. I'm going to rush through some. This is Ramanujan's first continued fraction constant. Let's note this bunch here now. We have 1, 2, 3, 4 equations, and in all 4 of them, we have the same structure on the left, but every other one's inverted. And they all have this 14. 1 to the 14th power. Then you square root it, so it becomes the 7th power. There's 4 of them. And then we have a batch of 1, 2, 3, 4, 5, 6, 7 more. 4 times 7, okay. They all have these 2 times square roots of 7 in there. So it's 14 divided by 2 square circles every time here, and then 4 pi over 32 all squared, which is a number connected into
the arrangements of temperatures of domain.
Yes, also the balance point in the zeta function.
Oh, yeah, that's
right. There's a balance functional inversion point in the zeta function there, which is cool. Also, now we move to the left, and now we're in 3-part sums. And let's just scroll through real quick so you can see whether your eye is noticing any connection. Do you see any pattern? Do you see any pattern? Now, remember, finding the pattern means you're being exposed to the language of reality, right? Because it's a pattern, in this case, of the constants of nature, which means it gives character to things that invert and persist. So these are the alphabet pieces available to physics. Okay, so this is really exciting, especially because it reveals the algebraic structure of the pieces, not just matching the number. Oh, great, we predicted the right kinds of numbers, but we still can't see into them. We can see into them with the algebraic connection they have.
Wait, what structure was that?
The algebraic structure.
Yeah, algebra is pretty cool.
Yeah. Yeah, okay, this is the fixed point of the hyperbolic cotangent, right? There's 2 fixed points in hyperbolic spaces, right? And cosines, sines, hyperbolic sines, tangents, hyperbolic, all that stuff. In all of them, you have a 0. If you put in 0, you return 0, or so your 0 is your fixed point. There's like 6 of those, right? But then we have 2 places. The hyperbolic cotangent has, so if you just write hyperbolic cotangent equals x, so of x equals x, it'll be this fixed point here. There's another one in the cosine, and it's the dotted number. Good. So those 2 things are just fixed points in hyperbolic division structure. Great. Let's move over to this column, which is 2-part sums or subtractions. Okay, and the very first one, which I hope if you've been watching this for a while, you're getting very familiar with now, is the speed of light, Planck length over the Planck time, which gives us the dimensions of length over time, right? A speed, and the numbers themselves give us the right value, and then you can now predict the value out to any digit you want. The inverse meter-hertz relationship is made out of the same components except for the inverse meters in there also. Same string of digits but different dimension. And in fact, many cases throughout the constants of nature, it turns out that there's another constant that has the same string of digits with a different stamp of dimensions attached to it. Okay, this is a huge clue. Okay, keep going down. I mean, Ramanujan's first continued fraction constant multiplied by 6. Now, if you don't know, we're talking about a system in that case that as it divides, it rotates once around a circle every time. It's a really simple division structure if you're modular. Okay, here we connect to our power tower. Now we have 5 delta Feigenbaum constants. These are the splitting coefficients, okay, in logic, and the alpha Feigenbaum constants. It's orthogonal twin. You got 1 over the lemniscate constant. There's 1 positive one for the atomic mass units. Okay, this is a derived unit of mass. And then we have 18 negative ones, and they're all exactly the same. Negative 1 over L, J1 minus J2, all the way down to here. And these are giving us another huge set of constants in nature. Okay, that's a gorgeous pattern. And so if you've never heard of the lemniscate constant, you should be very interested in it now, because it's holding together almost the entire mass boundary. The internal half of all of these mass expressions found in nature, right? The ones that all the actions of nature occur on, right there, lemniscate's have something there. All right, there's a whole row. Let's go to 3-part products. 1, 3, and 4. We're just getting familiar a little bit with what the structure looks like. Okay, and then we have squared 1, 3, and 4, and to the 4th power, and to the 8th power. Wait, what happened to 3, and 5, and 6, and 7?
Seem to be going up by powers of 2.
It seems to be going up by powers of 2. Power of 1, power of 2, 4, 8, and then it's done. Now, let's look at a symmetry here. From across this line, look how similar these 2 are. And then as we go, we got S, 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 S instead of pop, 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 right? But the structure is very mirrored here. And this is the charge over the electron, the Planck charge over the mass of the electron, and this is Planck charge over the mass of the proton. So it's a division. But we've jumped into 2, 3, and 4 here. Interesting. Single power, 2nd power, 1 triple power. All right. Now, perhaps the most simple and beautiful of all of them. This is the Planck energy in GeV. Notice we have 1 negative and 3 positive. So this gives the right signature for our 4-dimensional hyperbolic signature, right? And if we look at this other half down here, which is instead of being 1/2 real parts of the imaginary power tower times r squared, that means, and connecting that form on this boundary. So this is a central way of making this boundary, by the way, a central part of that boundary. Anyway, it has a signature, a sign of -1 and 3 positives, okay? So 1 negative, 3 positives is a sign. Then we go from real, 1/2 real, to 1/2 imaginary, and 4 of them, and the signature now is 1 positive and 3 negative, the exact inverse. So I'm imagining these are the 2 halves of the tower, I hope you are too, of an imaginary power tower twisting things together. I mean, you connect, rotation, connect. Now you're a bigger piece, and you rotate. Now you connect to another one, and rotate. Every time you rotate by 90 degrees, you connect to another piece, and now you connect the whole system, and rotate the whole system by 90 degrees. But that's what this is doing. All right, and we go below. Well, let's look here. There's a convention here I went with for naming the constants, okay? So if you look it up on Codata, this isn't the way they write the symbol for this, but it is how they write the name. And the name is Hertz inverse meter relationship. So the triple dots going up and down is in place for the word relationship in anywhere you see it here, okay? And left and right are the two things in the relationship. So Hertz inverse meter relationship. This is the atomic unit of velocity, atomic unit of momentum, and the natural unit of momentum. Or one noether?
Oh, one noter.
Noter.
Yeah.
Okay. Now we're jumping down from half imaginary power towers to whole imaginary power towers. Okay, and they're going to be negative, 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 negative. We got a positive one, another positive one, another. There's three, and any more? That's it. The rest are all negative. So on the right-hand side, other than the sign, these are all identical, right? Exactly the same. It's a beautiful, huge chunk of a pattern of the constants in nature that all take on the exact same internal structure. And what's their external projection? It's like a spiral where we're jumping down in steps, okay? And every step is just stepping from the electron mass, the muon, the proton, the neutron, the tau, the deuteron, the helion, triton, and alpha. Okay, that's the tower of masses here, smallest to biggest.
Well, these are all expressions of energy here.
Yes, and they're all expressions of energy because they're Planck length squared to Planck time squared.
C squared.
So the C squared, yeah. Which remember, C had the square root of the Giesking constant in it, and C squared then has. Okay. So this tower of energy, all held together by that spiral of I to the I to the I to the I, or I to JK, I JK, I JK, continues all the way down through many different constants, the joule-kilogram relationship, the kilogram-joule relationship, the joule atomic mass unit relationship. Beautiful. But I hope you're noticing, wait, the kilogram, the joule, these things are in the constants of nature? Yes, they're functionally built into the constants of nature. This isn't a unique claim by me. This is known by, I think, everybody who works on the constants of nature, okay? But here it is, built right in, okay? The electron volt is built right in. It's a derived unit from the decomposition structure, okay? All right, the electron volt, mega electron volt, let's see all the way down. We finished that column. Let's go up to, now this is a bipart. This one's bipart, r squared is also equal to 3 times 4. They're the same thing. So it's a bipart product. And over here, I got other bipart products, but the one at the top, you can write it many ways. You could write it as 1 over the square root of 2 pi times by r squared. So that's the bipart. The 3 and 4 is 3 times 4 is r squared. But I rewrote it this way instead because I think its full character is more informative. In fact, this Planck length, Planck mass for a Planck charge squared, if you made absolute values, it would be exactly the same as that thing. Okay, and this is the only constant of nature that says that, which means this piece, this one right here, is the most symmetric expression of the decomposition structure. Most symmetric because it's made up of only those pieces. It doesn't have other geometric parameters. It's fitting just its own pieces against itself. What do I mean? 4 pi, remember, is equal to negative j1 squared minus j2 squared minus j3 squared minus j4 squared. All 4 of them in the quadrants gives us a positive 4 pi if you have all minus signs. Or if you make it all positive, add them all together, you get negative 4 pi, right? Okay, so all 4 j's go into this geometric action on the left-hand side. And they're all squared. Okay, we take all the squares on the left, we take all the square roots on the right, and we just divide them so that they fit into themselves. And the system closes. And we get what's known as the magnetic constant. The magnetic constant, a beautiful, beautiful constant that also has one of the units in the logic structure we're talking about, the units of the decomposition structure of atoms, the meter, right in the balance. Okay. I'm not actually sure about this one yet. It's new. I'm still thinking about it, and how to connect that to this. So it might be wrong. I'm always willing to update anything here, right? But let's skip this one and look at the ones below it. Negative 1/6 and positive 1/6 times by the same J3, J4 over J1, J2. In fact, I need to go back to the board for a little bit. Okay, if we take J1, how do I want to do it? Yeah, J1 squared times J2 squared and divide it by 2 pi. It equals 2 pi divided by J3 squared times J4 squared. Do you see a supersymmetry here?
There appears to be some symmetry going on, yes.
Think if you have a throat that you're dividing about, but you're dividing about it from different ways. This is an inversion about the throat. Okay, also let's now say, okay, 2 pi is equal to 1, 2, 3, 4, all multiplied together. So let's take this equation here, and let's change the 2 pi to just J1 times J2 times J3 times J4. It's the same as 2 pi. Divide it by J3 squared and J4 squared. What happens? We cancel a J3 with one of those and J4 with one of those, and it equals J1, J2, J3, J4.
What?
Yes, it's also equal to this. So this is also equal to J1 over J2, J1 times J2 over J3 times J4. This is gorgeous. I mean, algebra has never been so beautiful as when you're looking at how the constants of nature are connected algebraically. Look at this. These are the partition solutions to the simplest projection of hyperbolic space. And look, they have an invertible structure that's just take the one-dimensional pieces, the one-dimensional product divided by the two-dimensional product. Gorgeous. And of course, this whole thing works if you turn everything upside down. So turn this upside down and this upside down and this upside down, and the statements are true also. So it's a really beautiful four-piece structure. Okay.
So what is that, 2 pi or what is it?
What? This one?
Yeah.
No, it's just J1, 2 over 3, 4.
Oh,
Yeah.
yeah.
And it's, I did it backwards. I can turn these upside down. I probably should. Let's do 2 pi over J1 squared, J2 squared, equals J3 squared, J4 squared over 2 pi. And that also equals J3, J4 over J1, J2. This is the place of supersymmetry in our decomposition structure, is my point. This is the place where this happens. Okay? You can code it, you can write about it this way, you can call it this way, or you can call it this way. They're all the same thing. And this is where this is where our division structure, right? In our most symmetric constant of nature, we have J3, J4 over J1, J2, all square rooted. That's the right-hand side of the magnetic constant. Okay, I think there was one other point to make there. Yes, there is. If we take this same structure and just ask, what's the other one if I say J3 plus J4 over J1 plus J2? Instead of multiplying, we just added them. Now, I, the imaginary unit. Okay. Anyway, it's a gorgeous algebraic system. It's a gorgeous algebraic decomposition system. But if you're trying to keep track of what it's talking about, then it's a gorgeous window into structure of reality, a window that lets you see the actions of physics. Now, I'm not saying we're all the way there. We haven't made all the animations. We're at the stage now where we're algebraically seeing. That's a level of seeing that is orders of magnitude beyond where we've been before. Okay, and it's going to open up windows that gives us access to, making sense of these things in ways that we can start doing things with them. More things we've done before. All right, so moving back to the screen. All right, moving on down here, here was our symmetry system I was talking about. And below here, we have that same symmetry boundary being divided up by 6 things in 2 cases. And in this case, this is interesting, 2 pi is j1 times j2 times j3 times j4, and jr squared is j3 times j4. So they mix very interestingly. It's like half of a circle plays with a whole circle, right? But 6 ways, and 6 ways again. So I hope you can see some sort of inversion happening here. You already know how this connects to a circle, okay? And then at the bottom of the pattern here, we get 36 circles on just one hyperbolic reach. Jr is, if you start from the origin and go draw a line out to J3 or to J4, the magnitude of that reach is Jr. Okay, moving on down, we have the ratio of the electron magnetic moment to the muon's magnetic moment. Depends on the mass of the muon and the mass of the electron, and on the right-hand side, the continued fraction constant and the 3-dimensional projection of our hyperbolic space. The continued fraction constant is the constant that defines the simplest step for dividing up. 1, then 2, then 3, then 4, and 5, as you go down the ladder. Okay, so if you're talking about a decomposition structure, that's a constant that you would like, okay, that's a great one to have, because you can tell what it means very clearly. All right, the cubes, we get some more complex cubes split into 3s and 4s. Notice with an 8 and a 36, an 8 and a 36, both over 2 pi here. So we have 8 s's, which is a lemniscate constant, the full arc length of the lemniscate, not the half, which is L, over 2 pi, and then with 36 over 2 pi. And remember, 8 times 36 is 288. The way we're breaking up our square sphere projected from our hyperbolic figure 8 knot. So a great start. We have a symmetry exchange happening internal and external with 2 hyperbolic figure 8 knots in our root for mass, the electron mass. Okay, really cool inversion happening there. I'm hoping if you've been exposed to constants in geometry before, that S and pi and L1 and hyperbolic figure 8 knot, and I'm hoping some of these parameters really stand out. If you're really versed in physics, maybe the mass of the electron and some of these other ones stand out.
Well, the other interesting thing too is the benefit of starting to understand some algebra and generalized mathematics is because you can also rewrite these things in different ways.
Yes, so you can rewrite any of these in a way that's equivalent if you think it's a way that you can see more into, and do it. Practice with it just to see the different ways. Cool thing here, this is new, right? Because the update from CODATA changed a lot for the electron mass. So, and a lot of things depend on the electron mass. The atomic mass unit depends on electron mass, and a lot of things depend on the atomic mass unit, and so on. So it's got a cascade structure. It changed, I don't know, a quarter, a third of the system, of the whole system.
4.5 sigma.
Yeah, because it was off by 4.5 sigma.
Now again, it was an extremely tiny amount in like the 11th and 12th digit there.
Yeah.
We got 10 digits, and that's a lot, but that tiny amount when you're dealing with from our scale, about a meter and dozens of kilograms-ish, that's a lot.
So that one was really hard for us in the sense, you're seeing a short form equation that's beautiful and symmetric and gives you the right number, but also propagates through the rest of the system that everything else depends on and gives the right numbers later too. So we had to try everything that could possibly be that was showing up in the patterns, and it took a long time to track, oh, it's just broken, now it doesn't work, through the system until we got the one that worked all the way. All right. I'm going to zip on down through here. You can just pick up on some of the patterns. We're staying in the R's. So I decided to represent this column in powers of R instead of 3 and 4 multiplied together, but they still represent that. It's just sometimes when you have an odd power, it's not 3 times 4 multiplied together anymore. That's only even powers. So the odd powers, you'd have to use a square root, so it was easier to represent this way. All right, and then the last column on the left begins with our natural unit of action, or reduced Planck constant. And this is a gorgeous, gorgeous set. Let's just watch it again. We've hopefully all seen this before. Not much has changed here, but I just want you to look at the system that's projecting all the parameters of action here. This is also a natural unit of action in electron volts, or electron volt seconds. Okay, the hyperfine transition frequency of cesium-133, and it has a special energy attached to it. So this energy is a scalar in energy, has units of energy, right? That's a constant we have to keep track of in our list. So this one's going to be on, all of these will be on the legend, but this is one of them that only shows up right here in one place. Here's the unit coulomb in both cases, the unit second, the joule, which is a composite unit of units, right? And we're still in the square root of theta 2, square root of zeta of 2. And zeta of 2 is also famously known as pi squared over 6, or 2 pi squared, 2 pi all squared over gamma of 5, 24, or there's many ways to write it. And they're all informative and helpful. And we're so far only multiplying all this pattern by theta squared. And theta is when you take from the origin and rotate out to the point 3, one of our division parameters, or to 4, you've rotated by an angle with a magnitude of theta. It can be positive or it can be negative. And this is theta squared. So we've got two natural rotations in our hyperbolic structure. This is the rotation that happens in our division structure. And two of them are playing a role here. And it's still 2 all the way down. And then we have 2 zeta of 3s instead of zeta of 2s that show up. All right, now another pattern with 6 e to the negative Euler Mascheroni over 6. Remember that constant showed up as a prime? It's a little different here with the minus sign and upside down, right? But it's very similar. It's got all the same pieces. And there's 6 of them. And they're all related to charge over electron, charge over proton mass, charge over electron, charge over proton. So this is a charge story. This guy has something to do with charge and primes. Very interesting. Well, how's a charge and prime connect? It's going to be a very powerful story, right? to reveal all that stuff. So the continued fraction constant shows up again with 6 circles. 4 of these with 6 circles. What might that be? And then you multiply the whole thing by 4. It's kind of a little bit reminiscent of our power tower already, but 3 domino tiling constant divided by 6, 4 plastic constants divided by 6, square root of them divided by 6, Madelung constants, lemniscates, and this is the derangement function, and red n is 5. So derangements of 5 means, and derangements are also subfactorials, so derangement of 5 is 44. Okay, this is it, guys. This is the pattern as we found so far, and here's the challenge. Go through the pattern to try to understand or to challenge, right? To try to say, this is a weakness, I don't think this part's right, we got to find something better here. Go through it to try to verify, try to see what it means. And if you can find anything that's wrong, send it to me, please. Point me to it, because I've been going through this all the time. I'm sure there's a typo somewhere. I'm sure there's a mistake somewhere. But I'm also sure there's ways to improve how we understand this, but it's going to require us looking into it further and telling more of the story. So we're finally at this stage now. I'm sorry it took so long, but there's been lots of changes happening day by day by day. We change, trying to get everything to fit. It's a difficult puzzle, and the ones with the most significant digits are usually the easiest to nail down. The ones that have the least, there's more choices, right, that it could be. So it took us till this point to get to here, but I hope you can appreciate that at this point, we have a simple story for the shape and structure of the simplest possible external projection of simplest internal manifold, playing the role of the gap structure for that external system. And these are the partial decomposition actions of that complete hyperbolic external projection. Here's the complete system right here. And the whole rest of the poster gives us the partial actions contained in that system, the things it can do and does. Not just can do, it always does. So the things it always has in it. So all of its internal properties. This full set of properties, you could say, aren't the things it does. It's what it is. right? They're not. It's the whole system, not just the internal things of the system. Okay. Anyway, that's where we're at. I hope you appreciate. Let me put up our supporters and helpers here. These are important people that have made this happen. And Matt, above all, has really, really been making this happen. Not just by supporting us, but by spending his time to support the concept, to make progress in it, to let his brain absorb the notions. And he's come up with lots of beautiful insights and ideas and questions, and he's been very successful at this. So anyway, thank you very much for the progress we've been making. You've helped with it. Yeah. Yeah, so I think this is very important. We would love your support. If you can support us by looking into this and trying to understand what's being said, it's extremely important. Why? Because at some point, when we learn how to turn this into machines, when we learn how to take advantage of this knowledge, which isn't going to be very far off now, that we have the actual insights, when we make sense of the logic right here, we'll be able to transform everything that atoms can transform on purpose. You'll have access to the things nature's doing with control. And that's going to change everything about the way we live, about the things we pay attention to, and the things that we feel held down by. Most importantly, we're going to move on to that Star Trek era, or I don't know what word you want to call it. It's going to be an era where we're not spending all of our time focused on the workday, earning money, doing things that we wouldn't otherwise do if we weren't getting paid for it. We're going to spend, I'm hoping and predicting, almost all of our human energy and conscious insight developing, growing into more, learning more day by day, because it's exciting to learn more. It gives you new powers. It gives you new ways to see things, but it gives you the ability to do more with more ease, right? So I think humans should be doing that all the time. We've long passed the time where we could, and this is going to bring us to the level of technology in which money becomes irrelevant, which I think is the most exciting. It's not a war where we have to get rid of money. It'll become irrelevant because you won't need it.
It's true post-scarcity.
True post-scarcity.
We're unlocking potential for the next generation.
Yeah. So anybody who's excited to help bring that future here, to help bring humanity to the point where money doesn't matter, not where you're taking anything away from anybody, where you're giving everybody the ability to understand how to get whatever they want simply because they understand how to transform the matter they're standing on. This is a really big deal. I believe it can happen. I'm not claiming it'll happen in my lifetime. I sure hope we can get there during my lifetime. But I believe we certainly can get there. Why? Because the hardest step was supposed to be to find the pattern in the constant's nature, to find the rules that are responsible for them, right? All the scaling parameters. And we now at a point where we have a pattern that I hope everyone watching could see. So that's it for now. Send us your comments if you can find any errors, you can find any improvements or suggestions. It's time to start participating in making sense of this. So,
Cool.
Thanks everybody.
Yeah.